Hey guys, and welcome to another video. So in this video I'll be talking about linear regression, and we'll be writing our own linear regression using gradient descent, and I'll show you the math behind gradient descent. So the linear regression is a tool that helps us find a linear line, in our case, to best fit a bunch of points, so that if you take each distance from each point to the line and square that, and then after that take the average, we're going to minimize that cost function. It's called a cost function. So gradient descent will help us iterate to the most minimal values of m and b so that the cost function is at its lowest. So next part of the video I'll be talking about the gradient descent and the math behind it. So I assume you know calculus, especially how to take partial derivatives which fall under multivariable calculus, and some knowledge of Python programming. But the key part is the math, so you should be concrete in your understanding of the concepts. So part 2 will be coming now. Okay, so here's part 2. So now I'm going to start talking about gradient descent. And first I'll talk about gradient descent, and then we're going to look at the math behind it. So the picture I have here is of some 3D bowl shape. It's not, I don't know if it's actually the graph of our cost function, but it's just some sort of bowl I kept up there. It might be the cost function, I'm not sure. But I know the cost function resembles some sort of 3D bowl. Okay, so we have this big bowl, and we start at a point, and our ideal goal is to keep on walking down all the way to the bottommost point of this bowl. That is where, for a certain value of m and b, the cost function is at its lowest point possible. So how do we keep on walking down to that bottom point? So this is where calculus comes into play. What we do is we look at not the whole bowl itself, but the graph of m and the graph of b independently. So this may or may not be the graph of m or b, but I just drew a parabola just to illustrate the concept. So imagine this is just the graph of m, just changing m's value with the other values constant, and this is how the cost function will behave with respect to m's change. So I just drew a parabola, and I'm going to walk you through the concept of gradient descent now. So imagine we're at this point right here, and our ideal goal is to come all the way down to this point, the minima. So we can just, if we want, we can just keep on like subtracting small values. So imagine my mouse is the point on the parabola. If we keep on just subtracting a really tiny value, it'll just go boop 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 all the way till it comes to convergence is what we call it, the bottommost point here, minima. But as you see, that took a long time. So what if instead these really steep parts we can take a bigger jump, and then on the small parts we start like taking tiny steps, because our minima is coming even closer and we don't want to jump too much so that we overshoot that minima. So this is kind of one of the neat properties of gradient descent. And if we look at this function, this expression right here, we take the slope at this point. So this slope is pretty steep, and what we do is we multiply it by this learning rate. This learning rate is usually a small value, and that usually changes. You play around to get that most ideal learning rate, and then we just add the negative value because we're stepping down. So it's kind of just subtracting to the current M or B value. So to walk you through that, this slope is pretty big. So we're going to take a bigger step. And then here, where we landed up now, we're going to, now slope is slightly smaller, so we're going to take a little bit smaller of a step. And then this slope is even more smaller, we're going to take a smaller step. So when we're coming really close to the convergence, it's getting like close, more flat and flatter and flatter. So slope keeps on decreasing. So every step we take now, according to this expression, is going to be even smaller until we keep on taking like really, really tiny steps to convergence. Let's quit that. So now we're going to see how do you find the slope at that point. That's where all the calculus starts coming into play. So, okay, so where we last left off, we're going to see how do you find the slope at each point with respect to M and with respect to B. So we're going to look at our cost function. So our cost function's right here. And as you can see, it's just taking the y value of the point and looking at the difference between that y value of the point and the y value of the line for each of those x values of the point. And then we square it so that we can get rid of any negative distances if the point is below the line, and also to like highlight bigger errors. And then we just, after we take all the sums, we just take the average of that. That's our cost function. And now we're going to see how this cost function will behave with respect to M and independently, and then B independently. So that's where partial derivatives comes in. So we're just going to look at this expression inside y minus mx minus b squared. And we're going to set that as f of I. And now we're going to try to see with respect to m, the partial derivative of this. So we're going to use the chain rule. So that small notation right here, like f prime, that basically just says the derivative of that function. So we can look at this function as two functions where f of x equals x squared, so, and then g of m and b is that inner part. So we can rewrite this equation as f of g of m and b. So this is the chain rule. I'm not going to talk about it too much except just use it. You can look on about this more on your own. And this is the formula that's given by it to find the partial derivative of the f of g of m and b. And now with respect to m. So f is going to be x squared, because we're squaring that inner part. And g is just going to be this inner part. So the derivative of x squared is just going to be 2x. And so it's 2 times g of m and b. That's what this is, right? And now the second part of this equation is the derivative of g. And now we're going to do it with respect to m. So we're going to utilize a property, the difference property, and we're going to split this up. So we're going to look at the derivative with respect to m of y minus the derivative of with respect to m of mx minus the derivative with respect to m of b. So with respect to y, it's going to just be 0. With respect to mx, negative mx, it's going to be negative x. I mean, just mx, it's going to be negative x, and because that's another rule. And with respect to b, it's going to be 0. So 0 minus x minus 0, that is just negative x. And so we get negative x for the second part of this expression. That's where this comes from. And then multiplying them together, we get negative 2x times y minus mx minus b. So I know I kind of just ran through this whole thing, but you can learn about partial derivatives more. So that's with respect to m. And then we take this back and we plug it back in. So instead of this. Now we're going to look at the partial derivative with respect to b. Okay, so now we're going to look at the partial derivative of the cost function with respect to b. And that's even simpler. And you'll see why. So we're going to use the first half of what we talked about in part 3. And now all we're going to do differently, instead of looking at the partial derivative with respect to m, we're going to look at it with respect to b. So coming back to that same difference property, so what's the partial derivative with respect to b of y minus the partial derivative with respect to b of mx minus the partial derivative with respect to b of b, and yeah. So with respect to with y, it's going to be 0. With mx, it's still going to be 0. And with just b, that's just b, and that's just going to be 1. And then 0 minus 0 minus 1 is negative 1. And then substituting back into that chain rule, the first part stays the same, but the second part, instead of it being negative x with respect to m, it's now going to be negative 1. And then that's how we get negative 2 times y minus mx minus b. And then we substitute that back into this part of the equation. And that's how we get both our partial derivatives. So now let's look at the code, and I'm going to walk you through this. So we're just going to import pandas to read our CSV file, and matplotlib to graph the lines and the points, pylab to graph the line, and numpy to help with making that line. Okay, so the first thing we're going to do is, well, all this I'm not going to really talk about. I'm going to talk about the main concepts. The other nitty-gritty stuff is not really important. So first we're going to read the data file and separate it with x and with y. So we get all the points that we want to best fit. We're going to just plot them on our graph using matplotlib. Okay, and then now this is our cost function. Our cost function really isn't needed code-wise, but it's just going to help us see the cost getting minimized. And here you can see this is the gradient function. So this is the main part of this code. So what that takes is L as the learning rate, M as the current M, and B as the current B. And we're going to set capital M and capital B as 0, but they will be the partial derivatives with respect to M and B. And we're going to do that simultaneously since we can look at them independently and step down with each independently. So here, the for loop, it's like the sigma. We're just going to go through all the points. And here you can see our partial derivatives that we derived in the previous parts of this video. So we can see negative 2 times n because we're taking the average. And then for b, it's just the negative came out. That's why it's negative right here. And then just y minus mx plus b. And then for m, it's the negative average. But here you can see our x comes because our partial derivatives, as you remember from here, from here was negative 2x. So the negative just popped out over there. And here's our x, and then here's just y minus mx plus b. And then after we calculate the derivative for all the points, we then return the new m, which is the slope at that point, which is symbolized by the capital M and capital B, times our learning rate, and then we're just subtracting that from the m and b values. So that's a step down. So we had to call this gradient function until we reach convergence. So that's where the iterate function comes in. That's just its main job. It's to just keep on calling the gradient function. So while true, it's going to keep on calling it. It's going to plot the current line. It's going to then call the gradient function with the current m and b values, get the result of that. That's what it returns. And then it's going to return that list of m and b, and then we're going to set m to be the new m value and b to be the new b value. And this is my way of checking for convergence. It's the temp m was the previous m and temp b was the previous b before we called gradient. So we're going to see if the difference that the new m stepped down, if it's less than this really small value, and same with b, that's where I'm just calling it a convergence, because it's now changing the m and b values super duper tiny, and that's where I'm just going to just break the loop. And then we just print m and b, and we're going to print the cost function, and then exit the code. So then here, we're just calling it the iterate function with a learning rate of 0.0002, and we're just going to set the initial m value to be -1, initial b value to be 0, and we're just going to send in all our points. So let's run this. So where we last left off, we were about to run our points, but then I ran into a small issue, and now we're going to actually run this. So I'm going to compile. My bad. We didn't get to see anything. So let me just run it. Okay. So now look at that. So you can see, I'm going to zoom in a little bit. Look at how the lines keep on, the shift in the line keeps on getting smaller and smaller. And this, that shows us that our gradient descent is working. And you can see that line that it's coming really close to, like the shifts now that it's doing, if I really zoom in, it's like super minutely just changing, looks like the b value. and now it's like almost at convergence. And this line does look pretty representative of all those points, so I'm going to say it's pretty good. Yeah, that looks pretty good. So our gradient descent is working, and it still hasn't reached convergence yet. But I can also show you, instead of plotting all the points, I can show you our cost function and how our cost function now, what is this? Oh, I think let's create a new variable I. Okay, so you can see our cost function now. It started at a really high value with the initial -1 and 0 as m and b, and now it's coming to be it's really decreasing, and here it's it shifts you cannot see, but it's just changing really tinily, and that's that. So I think that's enough. So you can see the implementation of a gradient descent and the math behind it. I kind of ran through that, but you can go back and look at a more detailed explanation on the internet. And that's it for now. Thanks for watching, and bye.